Hi everyone, the next topic that we are doing is properties of numbers. Now, in this topic, we have done some interesting concepts related to factors and multiples and all those ideas which we are going to apply in terms of last digit and everything. So, the first part, find the even number of factors for the number 2400. Second question, find the odd number of factors and so on. So 2400, the first thing, if you remember, for finding out the number of factors, we need to prime factorize that. When we prime factorize 2400, you can write it as 24 into 100 and then further break that down. Eventually, you will get 2 raised to 5 into 3 raised to 1 into 5 raised to 2. When you split all the factors as we had done during the concept part, this is what you will end up getting. And now, if you remember, we are supposed to find out not all the factors, but only the even factors. So for even factors, we need the even number. And out of all these numbers, especially even numbers are going to come from the powers of 2. And except 2 raised to 0. Because 2 raised to 0 is 1, which is not even. So except 2 raised to 0, if I consider any power, other power of 2, and if I multiply that with any other factor, I will get always a even number. So right from 2 raised to 1 till 2 raised to 5, there are 5 possibilities that we have. And those 5 possibilities multiplied with any other possibilities of the powers of 3 and 5 will give us the even factors. So 3 raised to 0 and 3 raised to 1, those two possibilities, and 5 raised to 0, 5 raised to 1, 5 raised to 2, those three possibilities. If you multiply all three, 5 into 2 into 3, that is 30 as the answer. So 2400 has basically 30 even factors. Second question, odd factors. Now for even factors, if we consider the even numbers, for odd factors, we should not consider that. So 2 raised to 1 till 2 raised to 5 will go off. That means from 2 raised to 5, the possibilities, we will have just one possibility, which is 2 raised to 0. And 3 raised to 0, 3 raised to 1, two possibilities. And 5 raised to 0, 5 raised to 1, 5 raised to 2, three possibilities. So that gives you the answer as 1 into 2 into 3, which is 6 odd factors. So 2400 basically has 36 total factors, out of which 30 are even factors and 6 are odd factors. This is how you can differentiate. Same question, how many factors are perfect squares and how many factors are perfect cubes? So this is where all the notes that we had studied earlier will come handy. Again, the first step is prime factorization and splitting all the powers. For perfect squares, if you remember the note, the powers has to be multiples of 2. And when you just list down the multiples of 2 powers, from the first set, you get 3 possibilities. 3 raised to 0, sorry, 2 raised to 0, 2 raised to 2, 2 raised to 4. From next one, just one possibility, 3 raised to 0. And from next set also, just two possibilities, 5 raised to 0 and 5 raised to 2. So for perfect square, the powers has to be even powers. That was the note. And when you just compile all of them, 3 into 1 into 2, there are total 6 factors of 2400 that are perfect squares. For perfect cube, if you remember the note, the powers has to be multiples of 3. But here we will add another layer to that and we will say that include the zeroth power as well. Because the zeroth power of any number is not going to change your answer. So include that as well. And that gives you a refined range now for finding out the perfect cube factors. That is zeroth power along with multiples of 3 power. So from the first set, you get two possibilities, 2 raised to 0 and 2 raised to 3. From second one, just one possibility, 3 raised to 0. And from the next one, another possibility, 5 raised to 0. So 2 is to 1 is to 1. That is total 2 factors that are perfect cubes out of 2400K, 2400K, 36 factors. So answer for that is option 3. Fifth one, how many ways we can write 1260 as a product of co-prime numbers? So you'll need to prime factorize that. Once you prime factorize 1260, you will get 2 raised to 2, 3 raised to 2, 5 raised to 1, 7 raised to 1. Now you just need to make the groups that are co-prime. Co-prime is numbers which have only one common factor between them. And when you just separate out the groups, these are the combinations that you can make it out. Consider one at a time, remaining three at a time. Keep swapping that. Once the 1 and 3 groups are done, make 2 ka groups. Three such combinations will be there for the alternate pairings. And then last one, most easy combination, 1 into the entire number. Now, obviously, in the exam, you won't be able to doing this much of mehnat. So we will give you a direct formula for this. But for that, the first step is still the same, which is prime factorization. You get the prime factorization wrong, the formula is not going to help you as well. So the formula for finding out in number of ways that you can write a particular number as a product of two co-prime factors is 2 raised to n minus 1, where n is the distinct prime factors, where n is the distinct prime factors. So for 1260, there are total 4 distinct prime factors, that is 2, 3, 5, 7. So the value of n becomes 4. 2 raised to 4 minus 1, that is 2 raised to 3. 2 raised to 3 is 8 ways. So this is how you can easily get this done. So you, most of the time, obviously, the question is how many ways you can write. So you can just use this formula as a 10, 15, 30-second shortcut. But if obviously if you require that in some of the question, you might that which are those ways, then you need to remember the original approach as well. So hence we are telling you both the things according to the situation. You can use one of them. Sixth one, if we have to extract the powers of 21 from 100 factorial, the maximum number of powers that you can get is. So obviously we cannot directly divide by 21 because that's not a prime number. So we'll have to split 21. 21 can be written as 3 into 7. So in short, we have to extract the powers of 3 and 7. But if you had paid attention to the concept part very clearly, you would remember that whenever such is the case, we will always focus on the bigger number, because 3 being the smaller number will always be more in quantity compared to 7 being a bigger number will always be compared to less in quantity. Individually 3 and 7 we don't care because we need them together to form 121. So the number of 21s, the matter of fact is that in terms of learning, that the number of 21s will not depend on number of threes, but it will depend on the number of sevens, the bigger number. Concept part we did, the number of tens will not dependent on the number of twos, because 2 being a smaller number will always be more in quantity. It will depend on 5 because 5 being a bigger number will always be less in quantity. Same idea here as well. So how do we extract number of sevens from 100 factorial? Forget the factorial sign, divide 100 by 7. That was the other shortcut approach. So 100 divided by 7, just note down the quotient, which is 14. Again, divide that 14 by 7, you get 2. Again, try to divide that 2 by 7. If you are getting the quotient 0, that is where you are going to stop. And whatever these answers that you have got, you are going to add all of them. So 14 plus 2, you get 16 as the answer. So there are total 16 sevens that you can extract from 100 factorial, resulting in 16 21s that you can extract from 100 factorial. Seventh one, number of 24s that we can extract from 60 factorial. Now, obviously, 24 again is not the prime number. So 24 needs to be broken down as a prime factorization, which is 2 cube and 3 raised to 1. Now here, obviously, we won't be able to do like in the previous case that we were looking at only at the bigger number. We are only going to do that when the mixing ratio is 1 is to 1. That is, for 121, we need 1 7 and 1 3. For 110, we needed 1, 2, and 1, 5. But here, such is not the case. For 124 to be made, we need actually 3 2s and 1 3. So the ratio is not 1 is to 1. And if such is the case, that means we need to first find out both of them, that in 60 factorial, how many 2s and how many 3s are there in totality, and then according to the requirement, make the groups and then compare the last part. So let's figure out how many 60s, sorry, how many 2s are there in 60 factorial. So 60 divided by 2, quotient is 30, 30 divided by 2, 15, 15 divided by 2, 7, 7 divided by 2, 3, 3 divided by 2, 1. That's it, because 1 divided by 2, you will get quotient 0, and that is where we will stop. So add all the numbers, 30 plus 15 plus 7 plus 3 plus 1. That gives you 56 2's are present in 60 factorial. But if you remember, for making a 24, we don't need 1 2, we require 3 2's. So these 56 2's need to be divided in the group of 3, because for 124, we are going to require 3 2's. So 56 divided by 3, maximum you can make 18 groups. Let's see how many 3's are there in 60 factorial. So 60 divided by 3, quotient is 20. 20 divided by 3, it is 6. 6 divided by 3, it is 2. 2 divided by 3, quotient is 0. We will stop there. Whatever the numbers that we have got, we'll add all of them. So 20 plus 6 plus 2, that is 60 factorial has 28 3's present in them. And for making 124, we require just 1 3 and 3 2's. So 56 2's, when we convert them into group of 3's, that means 56 divided by 3, maximum we can make 18 groups. And with those 18 groups, to make the 24, for each of the group, we are going to require 113 every time. That will give us the 24. So even though we have extra 3's, we have in totality 28 3's, we don't need the additional 10 3's, because for them to combine with, we don't have the group of 2's basically. So we will only take the 18 3's with each of the 3 2's ka group to give us 18 20. So mind you, whenever the ratio is 1 is to 1, only then you focus on the higher number and you get away with that very easily. But for such all these examples, you will have to find out both of the numbers that you are supposed to extract, and then according to the condition or the requirement, convert them into specific groupings and everything, and then proceed further basically. So that is the key idea that you need to remember. Eighth one is something that we had done in the question, I mean concept part already. Zeros at the end of 500 factorial. Zeros is tens, tens is 5. So number of fives at the end of 500 factorial, which is 124. We had already got that. Ninth one, if we subtract 3 from a number, then it becomes a perfect square. Then the original number cannot end in which of the following. तो ओरिजिनल नंबर का लास्ट डिजिट क्या नहीं हो सकता is what we are looking at. So just plot the equation. A number is there. When we subtract 3 from that, the resultant answer turns out to be a perfect square. And if it is a perfect square, then the last digit of that perfect square can be one of the following digits, either 0 or 1 or 4 or 5 or 6 or 9. Now we were wanting to find out the last digit of the number. So the only thing that we'll need to do is shift that 3 on the other side. So it becomes plus 3. And 3 being a single digit will be just simply added to the last digit of the perfect square. So the number will have, the last digit has either 3 or 4 or 7 or 8 or 9 or 2. But the question was, which of the following cannot be the last digit of the number? And I think from all the options, only 0 satisfies that criteria. Hence, option 5 for that answer. Straightforward question, very easy if you can just realize what kind of data you can plot here and get your answer. Last one, find the last non-zero digit in the following expression. So last non-zero digit. So first we need to confirm whether there are zeros or not. Clearly I can see there are a lot of zeros because zeros will depend on 2 and 5. I can see 25, so that means there are fives. I can see 2 in either 22 or 24 as well. So first we'll need to break that down. So 25 can be written as 5 square, and that 5 square raised to 13 will give you 5 raised to 26, laws of indices. Then 24 can be written as 3 raised to 12 and 8 raised to 12, but 8 can be written as 2 cube. 2 cube, the whole raised to 12 will be 2 raised to 36. So we have 26 fives and we have 36 twos, out of which 36 twos, 26 twos will go with 26 fives to make 26 zeros. Yani 26 tens basically. So the remaining 2 raised to 10 is as it is. So this is such a huge number that at the end part of this number, there will be 26 zeros. That is the interpretation of 10 raised to 26 at the last part. But if you remember, they were not asking the last digit because it would have been zero. They were asking for the last non-zero digit. This is where the idea of cyclicity and last digit will come into the picture, the concept that we have seen earlier. So 22 raised to 10, for us it is as good as 2 raised to 10. Find out the last digit of that using the concept. So when you do that, last digit of that turns out to be 4. For 23 raised to 11, last digit will be 7. For 3 raised to 12, last digit will be 1. And for 2 raised to 10, again the last digit will be 4 only. When you multiply these numbers, 4 into 4, 16. That is 6. 6 into 7, 42. Then a last digit of that answer has to be 2, which is answer option first. So the first part that you had to remember was to do the simplification, find out how many zeros are there first of all. And when you separate them out, then use the concept of last digit and cyclicity to get the final required answer. With this, we are done with properties of numbers. Thank you so much.